So for this video, guys, we're going to talk about 5.1, 5.2. Remember, once again, in your homework, it'll be called 5.1, but right now it says it's 5.2, so don't, read too much into that. So in chapter 1, we learned how to collect samples. In chapter 2 and 3, we learned how to display data from a sample in a frequency table and calculate statistics from data. In chapter 4, we learned how to find probabilities of certain outcomes. Now in chapter 5, we will learn how to create theoretical models describing how the experiment is expected to behave and then get its parameters. So this is the big thing. We're going to say, based on the information given, this is how it should work. This is what should happen. So this is kind of like that expectation. This is a very powerful tool in statistics because a lot of the times you can't gather all the information from every single possible individual in the study. Or I'm sorry, not in the study, but from the population. So what you do is you have to say, well, this is how things should work based on the data we have, or we can use percentages based on given circumstances and say, this is what should happen. Now, may it go the other way? Sure. But, if something has an 80% chance of happening, well, obviously 20% chance says it may not happen. But again, we're going to base our probabilities on that. So in the first part of chapter 5, we'll kind of learn how to do things the long way. And then in the second half of chapter 5, I'll teach you how to use a calculator. So definitely a calculator-based section. And chapter 6 will also be a heavy focus on calculators. So a random variable is a variable typically represented by X in this book that has a single numerical value determined by chance for each outcome of a procedure. A probability distribution is a description that gives the probability for each value X of a random variable. It is often expressed in the format of a graph, table, or a formula. So I think in this one, we're going to be given a table for this first problem. So it says 12 jurors are to be randomly selected from a population in which 80% of the jurors are Mexican American. If we assume that jurors are randomly selected without bias, and if we let X equal the number of Mexican American jurors among 12 jurors, find the probability that all 12 of the jurors are Mexican American, and find the probability that none of the 12 jurors are Mexican American. And here's the data for the probabilities given. So right now, we don't know how to find this information on our own. So they gave us a table to do it. Later on in the second half of this chapter 5, we'll learn how to find these probabilities without somebody giving them to us. Okay, so right now we're going to say probability that X equals what? Probability that all 12 of the jurors are Mexican American. Probability that X equals 12. So in this case, X equals the number of Mexican American jurors among the 12. So when we say X equals 12, we're saying the probability that all of them that are chosen for this jury are Mexican American. So we can look and we can say, well, we know, right, each jury, if we pick every single one. So what's the chance that the first juror is Mexican American? 0.8. What's the chance of the next one? 0.8. What's the chance of the next person? 0.8. And then the next one, 0.8. So this will actually be 0.8 to the 12th. Right? Which is approximately 0.0687 if we use 4 decimal places. Okay, so if you take 0.8 to the 12th on your calculator, you'll get approximately 0.0687. Okay, then it says find the probability that none of the 12 jurors are Mexican American. Well, think about it this way. If the probability of being Mexican American on the jury is 80%, what's the probability of not being Mexican American? It would be 20%. So we're going to say the probability that X equals 0. So that would equal 0.2 times 0.2 times 0.2. So similar to above. And this would be 0.2 to the 12th. So 12 people chosen, all 12 of them are not Mexican American. So if we plug this in, we get 4.09 times 10, times 10 to the negative 9. So remember, once again, I probably should have rounded this one off, to be honest. I should have probably done 3 decimal places, 0.069, because I did 3 decimal places or 3 significant digits on this one, but that's okay. But just so we're clear, you guys, this is a very small probability. right? Because 4.09 times 10 to the negative 9 is 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this number right here represents the probability of that actually happening. So you see how it's almost zero? That's almost zero. In your book, they write it as 0 plus sometimes. So you see all these 0 pluses? That means that it's not actually zero. It's not actually zero, but it's so close to zero you can't, tell the difference. It's a very, very small probability. Now notice here we have 0.069. That's the same probability I got here because that was all 12. And then notice here, I got a very, very small number close to zero. So for no Mexican American jurors, they gave us 0 plus. And remember, once again, 0 plus signifies basically zero, just a little bit above zero, but so small that they almost call it zero. Okay, so this is how I did it here, but I could have also used the table. Now, what if they had said 7 Mexican American jurors? Well, I can't do it the same way. I would actually have to rely solely on the table because I couldn't do it by hand right now. I don't have the tools to take care of that problem. Okay, so the reason they asked us these two is because right now, those are the only two that you could do by hand that you don't need the table. But as you can see in the table, it still gave us the information. Okay, and we got it to match. So now it says the table gives the probability for each value in random X variable. So this is saying what's the probability of 5 jurors being Mexican American, of 8 jurors, of 11, so on and so on. You can pick any number and this table gives you those values. And it's based on the fact that there's a 80%, you're choosing from a pool of 80% population of Mexican American for this particular jury. So a variable that has finite or countable lists of outcomes is called a discrete random variable. A continuous random variable has infinitely many values and collections of values is not countable. Identify whether the variable in the following is discrete or continuous. So this goes back to, I think it was almost section 1, chapter 1 or chapter 2, talking about continuous and discrete. So let X be the number of students present for this class on any given day. This is definitely discrete. Right? Because no matter how you rearrange it, there's a certain amount, there is a certain way you can count. Let's say 35 students show up to class. There's only one way you can count that there's 35, right? Now this one, height of a pine tree. Now somebody that has a really accurate measuring tool might get a different height of the pine tree than I got if I was using like a meter stick. So again, this is what I kind of help. This was how I decide if something's discrete or continuous. So this is continuous because the height of a pine tree could be, 37.2817 feet, or it could be 32.81752683 feet, so on and so on. So this is a continuous random variable. Okay, so let's move on. So it says there are many ways to graph probability distribution, but the most common way is through a probability histogram. A probability histogram is much like a relative frequency histogram that was discussed in chapter 2. The horizontal axis will have the values of the random variable X. So here's our 0 through 12 jurors. And then this is our probabilities. What's the probability of these outcomes? Okay, so construct a probability histogram for the probability distribution from the previous table. So we're going to go for 0, X equals 0 jurors that were Mexican American. So 0, 1, 2, and 3 all have no jurors. So let's go here. Let's go here. Let's go here. Okay. Then you know what I'm going to do? I'm going to make it the midpoints. No, I don't think that'll look quite right. I guess, you know what? Let's just do this. Okay, so there's the 0, right? So 0 through 3 is none. And then let's do 4. What's the probability of 4 people on the jury that are Mexican American? 0.001. So I can't even barely see it. I'm just going to, just for sake of drawing, I'm going to put it there. And then for our 5, 0.003. So that's just a little bit higher. And again, it's actually even smaller than this. I just, for the sake of drawing, I'm going to try to draw it. And then for 6, 0.016. So once again, very, very small. And then 0.053, so that is about halfway. Okay, and now 7 would be 0.053. Oh, we already did 7. Now let's do 8. 8 would be 0.133. So here's 0.1, so it's actually up here. And then for 9, 0.236, so that would actually be here. And then for 10, let's see what we got. 0.283, that's almost to the very top at 0.3. Okay, and then let's look at 11 is 0.206, so that's right about here. And then 12 would be 0.069, so we're back to way down here. So that would be our histogram, give or take. I could have used midpoints and maybe it would have looked better, but you get the idea. So this would be what we would call a left skewed histogram, okay, or left skewed data. So requirements for probability distribution, that the sum of all the probabilities is equal to 1, and each of the individual probabilities is in between 0 and 1, which makes sense. You can't say that something is -% chance to happen, and you can't say the probability of something occurring is more than 100% or more than 1. So here we have another example using a table. And again, we're going to use tables for now because we can't figure all this out on our own. We're going to get the tools for that in the second half. So choose a person age 19 to 25 years at random and ask, in the past 7 days, how many days did you go to an exercise or fitness center or work out? Call response X, the number of days the person worked out. Here's the probability model. So here's the model that's already been built for us. So we have to verify that this is a legitimate probability model. So I have to add up all the probabilities. So I'm going to do 0.68 plus 0.05 plus 0.07 plus 0.08 plus 0.05 plus 0.04 plus 0.01 plus 0.02. Oops. Let's see. This is 0.1. And this is, let me see, 0.17. 0.27. Oops. So I'm just going to add them up. I'm trying to do it in my head and it's not working. So this will be, if we add these up, that'll be 0.73. These two combined with this one, that will be 0.2. This and this will be 0.05. And then, well, I guess we'll do all three of these. 0.07. So that would be 0.27 plus 0.73, so 0.73 plus, yeah, so this will end up being, so 0.68 plus 0.05 plus 0.07, I don't know why I erased it, 0.08 plus 0.05 plus 0.04 plus 0.01 plus 0.02 all adds up to 1. Check. Then the second thing is this, so this is the first check. The second check would be all of the P of X's are less than or in between So all the probabilities are between 0 and 1, so that's good. And it says describe probability of X less than 7 in words and find the probability. So probability that X is less than 7. Well, remember, X stands for the number of days they worked out in the last week, okay? So less than 7 means all the days probabilities added up that are not 7 days working out. Okay, so think about this. That means we have to add up this probability, this probability, this probability, this probability, this probability, this probability, and this. We don't add up this one because that's 7 days, not less than 7. So that would mean we do 0.68, or I could just do 1 minus 0.02, which is the 1 day we don't use, right? And that'll give me the rest of the probability, so it'd be 0.98. Okay. Let's see here. Part C, express the event worked out at least once in probability terms. What is the probability? So the probability you worked out at least one time, wouldn't that be the probability that X is greater than or equal to 1? Because you're saying I worked out 1 day or 2 days or 3 days or 4 days or 5 days or 6 days or 7 days. Any of those days count. So when I want to find those probabilities, that's going to add all the days up that are greater than or equal to 1. So that means I'm going to do 0.05, 0.07, 0.08, 0.05, 0.04, 0.01, and 0.02. I'm going to add all these up, and I should get 0.32. Or alternatively, I could have done it this way. Probability that X is greater than or equal to 1 is equivalent to 1 minus probability that X equals 0, right? What's the probability that X equals 0? 0.68. So this would be 1 minus 0.68. Which equals 0.32, same answer. But this one I use the total probability, right? Remember we talk about everything has to add up to 1. And in this one I added up these days right here, okay? So that's how we can work with that. So mean, variance, and standard deviation. The probability histogram can give us an idea of the shape of the distribution as to where the center of the distribution is. However, we can find the mean, variance, standard deviation of data through calculation. So again, we're going to do this the slow way for now, and then eventually we'll have other ways to do it down the road. Okay, so wait a minute. Did I do the wrong page? No. Okay, sorry guys. I thought I skipped a page. So don't stress too much about these formulas. Basically, I'm going to show you how to do them right here. So in order to find the mean, and again, the mean for probability distribution is a big deal. Mean in general in this class is a big deal, and so is standard deviation, which in turn means that variance is a big deal, but we'll really focus much more on standard deviation for our course. It says find the mean of the distributions. Well, in order to find the mean, in order to find the mean, it says that we have to do mu is equal to X times all the P of X's. So that means I have to multiply every single one of these P of X's times the matching X. So that means if I want to do the mean, let's write it right here. Okay, I have to do 0 times 0.68, which is 0. I have to do 1 times 0.05, which is 0.05. I have to do 2 times 0.07, which is 0.14. This would be 0.24. This would be 0.20. This would be 0.20. Oops. This would be 0.06. And then this one would be 0.14, I believe. And then what we do is this symbol, remember, means to sum. So we're going to add all these up. And when you add all these up, so I'm going to find the mean is equal to 0 plus 0.05 plus 0.14 plus 0.24 plus 0.20 plus 0.20 plus 0.06 plus 0.14. When you add all these up, you should get 1.03, okay, if I did everything correct. So this is our mean. So mu equals 1.03. It says find the variance of the distribution. Well, according to this, in order to find the variance, right, the variance of the probability distribution, you have to square all the x's, multiply it by P of X, and then add those up, and then subtract mu squared. Okay, so we're going to do that, but I'm going to do that down below here. So now this is going to be variance. So this will be x squared times P of X. I'm going to put that for right here. And this was x times P of x, right? So x squared would be 0 times this would be 0. X squared would be 1 times this would be 0.05. X squared would be 4 times 0.07 would be 0.28. That would be 9. That would be 0.72. That would be 16 times 5. That would be 0.80. That would be 25 times that. So that would be, I think, 1. Yeah, 0.25. I'm sorry, 25 times 0.04 would be 1. The next one would be 36. So this would be 0.36. And the next one would be 49. So that'd be 0.98, I believe. Now I have to add all those up, right? So I have to take 0.05 plus 0.28 plus 0.72 plus 0.80 plus 1 plus 0.36 plus 0.98. And then I have to subtract off 1.03 squared, right? Because that's what I'm doing right here. I'm subtracting off the mean squared. So this will become, find the variance. So the variance, squared is equal to 4.19 minus 1.03 squared. So let me do this on my calculator. 0.05 plus 0.28 plus 0.72 plus 0.80 plus 0.36 plus 0.98. So I get 4.16. Did I miss something? Let me see here. Oh, that's 0.28, not 0.25. Sorry about that. It's going to be off a little. I messed up. 0.28. So I get 4.19 minus 1.03 squared minus 1.03 squared. And that will equal 3.1291. But I'm just going to round it off to 3.129. And that will be our variance. Now, what if they ask us for the standard deviation? Remember, standard deviation is just the square root of 3.129. Second function. So second function square root of 3.129. And I get 1.7688. So I'm going to call it 1.769. So I get 1.769 days. Okay. So that's how you can find the standard deviation, the mean, and the variance all by hand. And you just use these three formulas. And this is, again, you don't want to do this a bunch, but this is how you could do it. Okay. So now determining unusual values. Just like before, the rule of thumb is minimum usual value is the mean minus 2 standard deviation. So we've already done this. This is just now combining it into this chapter. Okay. So working out, using the rule of thumb for usual values, what is the range of usual values for number of days someone has gone to an exercise or fitness center in the past 7 days? So what we do is we know that it is, so min usual is equal to 1.03 minus 2 times the standard deviation, 1.769. And that is approximately equal to, let me go over here. So this is the minimum usual values. Let me see here, 1.0, minus 2 times 1.769, negative 2.508. Max value would be 1.03 plus 2 times 1.769, and this would give us 4.568 days. So these are both days, right? Okay, so obviously we can't have a negative. So sometimes you can just think of this as 0 because you can't work out less than, 0 days. So it says So basically, we can't really have a minimum usual in this term because you can't work out less than 0 days. So it says, is it unusual for someone to say they have worked out all 7 of the past 7 days? Yes, it is. Our maximum usual number of days to work out is 4.568 days. So if they say they've worked out 7 days a week, that is unusual based on the data we have, based on our not data, based on our model for the outcomes, okay, or our predictability, okay. So I basically just created this to say if you work out in between these amounts, you should be good. So that also means somebody that works out 5, 6, or 7 days is considered unusual in terms of this, okay. And again, don't think unusual is bad. Working out more than 4 days a week is good. That's great. But I'm just saying, it's considered in our problem unusual. Okay. So rare event rule, if under a given assumption, such as the assumption that a coin is fair, the probability of a particular observed event, 992 heads out of 1,000, is extremely small, we conclude the assumption is probably not correct. Okay, I think there's a typo in here. So let's fix this real quick. I think there's a typo right here. Cross that out and put less. So unusually high number of successes, X successes among N trials is unusually high number of successes if P of X or more is less than 0.05. And unusually low number of successes is X success among N trials is unusually low number of successes if P of X or less is 0.05, okay? So based on the rare event rule, is the event of an individual working out at least 6 days out of the past 7 considered unusual? So we have to think, what does at least 6 mean? Well, that's the probability of X greater than or equal to 6, right? Because it could be 6 days or 7 days. So we have to take the probability for 6 days. 6 days would be 0.01 and 0.02 for 7. So we do 0.01 plus 0.02, and that equals 0.03. This is less than or equal to 0.05. Therefore, the rare event rule states the assumption is probably incorrect. Let me fix this pen too. Okay, so because it is less than 0.05, we normally say less than or equal to 5% or less chance of it happening. We normally say it's unlikely, more than likely your assumption was wrong from the beginning. So the probability of working out 6 or 7 days a week is unlikely when you talk to this individual, okay? But is the event of an individual working out at least 5 days out of the past 7 considered unusual? So let's see, at least 5. Probability of X is greater than or equal to 5. Now that would be, let's do 5 days. Where's that at? 0.04, 0.01, and 0.02. 0.04 plus 0.01 plus 0.02. I think I wrote it out of order, but you guys get the idea. Oh no, that was right. So this adds up to, what is that, 0.07, which is greater than or equal to 0.05. So is the event individual working out less than we consider? No. And once again, by rare event rule. I can't write today. Okay. So that would not be considered unusual, okay? Let's see here. Expected value. The mean of a discrete random variable is a theoretical mean outcome is the theoretical mean outcome for infinitely many trials. We can think of that mean as the expected value. That is the average value. We would expect to get if trials could be continue indefinitely. So basically what this is saying, there should have been a comma in there somewhere. I just read it bad. Basically what this is saying is that if you can find the expected value, or I should say, if you can find the mean, that is actually the expected value, okay? Which makes sense. Like I told you, if you ask people that took my class, what was the mean of the class, and they said, oh, an 82%. Well, then if you took the class, you would expect to get an 82%. Now you could do better, you could do worse, but the expected value is often thought of as the mean, okay? So it says the local library allows checking out up to 5, but, and by the way, does this formula look familiar? It's the same formula up here for mean. They're the same formula, okay? So whenever you hear expected value, that's kind of statistics code for, hey, find the mean. So it says the local library allows checking out up to 5 books at any one time. Based on historical records, X equals the number of books checked out by an individual has the following population distribution. Check if it's legitimate first, okay? So we're gonna add all these up, 0.20 plus 0.32 plus 0.18 plus 0.15 plus 0.10 plus 0.05. Let me see, 0.52, 0.7, 0.95, yeah, so this adds up to 1, and then, so check, and then all probabilities are between 0 and 1. All the probabilities right here are between 0 and 1, so it's okay, so check. Find the expected value. So again, on the test, I probably would not say find the expected value, also known as the mean. I would say, hey, find the expected value, and you have to know that the expected value is the mean. So in order to find the mean, remember we just did this, we did X times P of X and then added them. So this is going to be 0. This is going to be, let me write it in green. This is going to be 0. This is going to be 0.32. Let's see here. This will be what, 0.72. This will be 0.45. This will be 0.4, and this will be 0.25. Let me just double check and make sure that's right. Yeah, it looks good. Oops, I think I got one wrong. I don't know why I squared the 2. Yeah, this is supposed to be 0.36. Sorry about that, you guys. Okay, so in order to find the expected value, all we do is we add all these up. So mu equals 0.32 plus 0.36 plus 0.45 plus 0.40 plus 0.25. And let's see what we get. $1.78 is our expected value. And this is 1.78 books. Okay. All right, you guys. So that's the first half. Let's see how much more there is. So we have basically 1, 2, 3. Let me see how many pages. 1, 2, 3, 4. Okay, so I think that's enough for the first video. I'm going to post that today, or I'm going to post that at some point. And please let me know what you guys are struggling with, and we'll talk about it during our meetings.